Hello, chemistry students. This is Professor Sean McMahon with our fourth lecture on Chapter 6, Compounds and Their Bonds. So in the first lecture, we focused on determining whether something was an ionic compound from a complete exchange of electrons, a metal losing electrons, nonmetals gaining, or a molecular compound, covalent compound, where there's a sharing of electrons between two nonmetals. After discussing the different types of bonds and how to name chemical formulas and how to write out formulas from names, we then went on to Lewis dot structures and actually drawing, using the Lewis dot structures and the rules that were taught, drawing these molecules in a two-dimensional diagram. From there, we went on to molecular geometry, where we try to show the 3D shape and understand the valence shell electron pair repulsion theory, where how we look at electron groups around a central atom and how they arrange themselves in space to minimize repulsion. And as a result, you get a three-dimensional structure. And then we focused on, well, if I have a three-dimensional structure, it's going to give me some type of polarity. Polarity being whether the molecule is asymmetrical versus symmetrical, where it would be a non-polar molecule. Typically, again, with Lewis dot structures and molecular geometry, we're looking at covalent bonds. Covalent bonds are found in covalent compounds, but also polyatomic ions. Now, they're ions because they have a charge overall, but they're held together covalently. So today, we're going to use all that information in our last lecture, and we're going to apply it to something referred to as intermolecular forces. Everything up to this point has been the bonds within a molecule. We are going to expand that understanding and use our concept of polarity to understand how molecules interact with one another. So as a quick review, we'll go over molecular polarity where we left off last time, and then we'll go straight into intermolecular forces. So in compound number 1, we see that this hydrogen chloride has a dipole moment signified by the arrow schematic here. The arrowhead is showing where the electrons are being pulled. So the electrons are being pulled towards the chlorine. It is more electronegative, so it has a partial negative charge, where the hydrogen has a partial positive due to this electronegativity difference. But the easiest way to determine whether or not this molecule is polar or nonpolar is hydrogen chloride symmetrical? And the answer is no, it's asymmetrical. So it is a polar molecule. If I go to molecule number 2, ammonia, what is missing, because typically when you do these ball and stick models, you only include the atoms as electron groups. You do not include lone pairs. We actually have a lone pair over the nitrogen so that the nitrogen actually has its octet. That lone pair is an electron group, and that's why we must use that for determining our valence shell electron pair repulsion theory, that there are actually 4 groups around this nitrogen, the central atom, and the 4 groups show an electron group geometry of tetrahedral. Now, the molecular geometry only looks at the molecule and doesn't take into account the lone pair. So this would be pyramidal. But for the most part, what you want to do is to determine whether this is a polar or non-polar molecule is to see if there's symmetry. And in actuality, it looks symmetrical, but it actually isn't, because you have a 4th group that is not identical. This lone pair is not the same as these 3 hydrogens. So because of that, this is a polar molecule. It lacks symmetry. Now you can also use the dipoles and use their vectors, kind of their magnitude, to see overall they wouldn't cancel out, and I would have a net dipole moment going towards the nitrogen in this molecule. Okay. When I look at molecule 3, okay, so you can think of this as a symmetrical molecule. It's basically carbon tetrachloride, and it has, even though it has 4 bonds that are all polar, if you look, The carbon-chlorine bond, chlorine is more electronegative, it is more polar, it's pulling the electrons towards it. Because this is symmetrical and all four groups in this tetrahedral arrangement are the same, this is a non-polar molecule because it's basically symmetrical. If I look at the boron trifluoride, there's three groups. Now, boron's an exception to the octet. I had mentioned this before. So there's actually no lone pairs on it. I only have three groups in this trigonal planar arrangement, and they're all within 120 degrees of each other. So that makes this a symmetrical molecule, and that's why it's nonpolar. If I look at number 5, again, I have examples of nonpolar bonds between the carbon and hydrogen, but I have this one polar bond between the carbon and chlorine. That's why we see the dipole. So we see that there's a partial negative charge, and overall in this molecule, there's a dipole going towards the chlorine. As a result, this lacks symmetry. An easier way to look at it is the 4 things attached to carbon are 3 hydrogens and 1 chlorine. So this lacks symmetry. It's asymmetrical. There's not 4 chlorines or 4 hydrogens. There's something that's different. So this would be an example of polar molecule. Now we're going to use this polarity in molecules to understand something a little bit bigger, and that is electrostatic forces. So every molecule in matter experiences 2 types. Okay, and electrostatic forces, you can think of it as positive repel, negative repel. That's kind of why we did the valence shell electron pair repulsion theory, is to minimize the electron group repulsion. But we also learned that opposites attract, right? So we have protons and electrons that attract each other. So the bulk of this chapter so far has focused on intramolecular forces. That's the forces within the molecule. So in this case, you know, primarily with Lewis dot, it's the covalent bonds, whether they're polar or nonpolar. But you can also think of ionic bonds, even though there's a complete electron transfer, as an intramolecular force. Inter is the force between molecules. So an international flight is between countries. Inter, which means between, is the force between molecules. And it's this force that's going to determine physical properties. So they originate from the reaction or the interaction of charges or partial charges. The intermolecular forces that are between molecules are weak compared to the bonds that hold them together. And part of that has to do with the distance. So here I have a picture of 2 water molecules. Again, the oxygen's in red and the hydrogens are in white. It's bent because there's 2 lone pairs, and the electron group geometry is tetrahedral because there's 4 electron groups, but the molecular geometry that only takes into account the atoms is bent. And what we notice is that the oxygen and the hydrogen are sharing 2 electrons in this bond. That's what a covalent bond is. It's a shared pair of electrons. But because the oxygen is more electronegative, it's pulling the electrons towards it, and that's why it's partially negative, and the hydrogens are partially positive. When we look at the intramolecular, this polar bond, okay, when we're talking about the electrostatic forces, is both the oxygen atom and the hydrogen atom have protons in the nucleus. And then the electrons in this bond are attracted to those protons, right? Because opposites attract. But because the distance is smaller, that attraction is a lot greater. You can think of it as magnets. As magnets are really close, it's harder to pull them apart because they're close. As they get further apart, it's easier to pull them away. That's why intermolecular forces are weaker than intra. Intra are the bonds that exist within a molecule that keep it together. Those are much harder to break. Intermolecular forces are between molecules, and they're easier to break because there's a greater distance here. okay? So what is the intermolecular force? This hydrogen has a partial positive charge. The neighboring oxygen has a partial negative charge. What do we say electrostatic forces are? There were charged particles or partially charged particles are attracted to each other. So this partially charged particle is attracted to this because of the greater distance, and it's not within, it's an intermolecular force. So it still causes the water molecules to stick to each other. So since we're talking about intermolecular forces influencing physical properties, one of the physical properties of matter is it a solid, liquid, or a gas? Well, that depends. It depends between the intermolecular forces, the strength of them, and the kinetic energy of the molecule. And kinetic energy, if you remember, is associated with movement when we talked about the forms of energy. So it's basically a battle. So what is going to dominate? Is the kinetic energy stronger than the intermolecular force attraction? If that's the case, it's going to influence what state of matter we find it. So again, recall that the average kinetic energy of a sample is related to its temperature, and we call that thermal energy. So let's see who wins the battle. So with gases, the particles are far apart, they're moving fast, okay? And that movement, that energy is much greater than the intermolecular forces that would cause them to stick together. That's why if the intermolecular forces are weak, there's nothing that's holding the particles together. They're not very sticky, so they fly apart. So in gases, kinetic energy is much stronger than the intermolecular forces. That's why they don't stick together, and the majority of space of a gas is empty space. In a liquid, there is kinetic energy, but the intermolecular forces are stronger. So what happens is it causes sticking of the molecules, but there's not so much sticking that they can't slip and slide. So there is movement, and that's why liquid, like water, you can pour it, right? It runs downhill. So with liquid, there is movement, but the intermolecular forces are now stronger, so it causes sticking. That's why they have constant volume, but they can slip and slide over each other, and that's why it moves. Kinetic energy. With solid, the kinetic energy is very little, okay? The intermolecular forces are so strong, the particles are stuck in a constant volume in a static state. However, there's still movement because we know that there's vibrational energy, right? So atoms are vibrating, right? The nucleus has protons that are spinning along magnetic fields, and the electrons are in their orbitals moving around as well. So there's still vibrational energy, but it's stuck in a static, fixed shape and volume. So that's what this is basically showing. Solids, intermolecular forces are extremely strong, very little kinetic energy. Liquids, intermolecular forces are strong, there is some kinetic energy. Gases, intermolecular forces are weak, there's a ton of kinetic energy and movement. So the major difference between gases and the other two states, liquids and solids, which are referred to as condensed because they have a fixed volume, is the distance between the particles. Gases have a major distance, okay? Condensed phases, liquid and solid, have fixed volumes. Now, liquids do not have a fixed shape because, again, they have that movement of slipping and sliding. That's why you can pour 100 mils in a cup or a bowl, but it has a fixed volume. The major difference between liquids and solids is the freedom of motion. Liquids slip and slide, solids static in a fixed lattice structure. So what are some of the properties of liquids? They have high densities relative to gases. And if you remember, the density of water, the only density you need to really memorize is 1 gram. Sorry, my pen's not working. 1 gram per mil. So we see that the units are grams per mil. Their shape can change. but their volume is constant. They cannot be compressed. Solids, they typically have densities of grams per mil as well. They're high. You know, if you think of the density of aluminum, aluminum's a solid. It's 2.7 grams per mil. That's greater than water, which is 1 gram per mil. That's why if you drop an aluminum rod into water, it will sink to the bottom, okay? They have a definite shape. Notice I said aluminum rod, it's a shape, and their volumes are fixed as well. They can be crystalline or amorphous. Remember, crystalline is a repeating pattern. So you can think of salt crystals. Amorphous is unordered, and there's some flexibility. You can think of rubber, plastic, glass. So what's going on? Why is something condensed? You know, what's keeping it in a condensed state? Well, and keeping them close, the intermolecular forces. So the intermolecular forces are further apart, and they're the attractive forces. And again, where are we noticing the attraction? Neighboring molecules. This oxygen has a partial negative. This hydrogen has a partial positive. So those temporary charges have electrostatic forces. Now, with the intermolecular forces, the distance is greater. Therefore, it's weaker than the intramolecular forces within the molecule. That covalent polar bond is much stronger than this, and we'll learn hydrogen bond. But the hydrogen bond, this intermolecular force, is strong enough to keep these particles together and in a liquid state. So we're going to consider 3 types to start. First, we're going to consider the dipole-dipole. Then we'll discuss the hydrogen bonding, which is essentially a super dipole, okay? And what that means is we have super small polar molecules exhibiting hydrogen bonding. Then we have dispersion London forces. We'll see that all molecules experience the dispersion forces, but they're the predominant force when I have either small non-polar molecules or very, very large molecules. And you may, if you've taken biology, they typically refer to dipole, and dispersion forces as van der Waal interactions. Or you may have heard hydrophilic and hydrophobic interactions if you've taken biology, okay? But let's start with dipole-dipole. It's an attractive force between polar molecules. Now, why is that? With a polar molecule, you have what is referred to as a permanent dipole, okay? So if I draw chlorine, which has 7 valence electrons, and fluorine, which has 7 valence electrons, they have 1 odd electron, and they need 1 more, so they're willing to share that in a bond. There's a bond right there. I'm sorry, my pen's, there it is. It's going in and out. It's the internet connection. But there's a bond right there. The reason why they have a partial negative on the fluorine, it's more electronegative, so it can pull the electron, creating this partial negative charge. And then with the chlorine, it has a partial positive because the electrons are being pulled away towards the fluorine. So this is a permanent dipole. It always is there. So what happens, because this is always partially positive and this is partially negative, these are going to be in the neighboring molecules lining up. So what would that look like? Well, if I have a neighboring molecule, now it's going to align itself where the chlorine is next to this fluorine and the fluorine is next to this chlorine. And that's what we see here. So with polar molecules, you have partial positive and partial negative ends. The opposite poles attract, and that is why we see these opposite poles in neighboring molecules aligning themselves so that the dipoles put opposite to opposite, because opposites attract. The more polar a molecule is, the higher the boiling point. So what are we doing here? We're relating intermolecular forces to a physical property. When we first learned physical properties, three of the most important physical properties we discussed were density, boiling point, and melting point. Okay, so now the reason why we're bringing up boiling point is for something to boil, you have to go from a liquid state to a gas state. Now remember, the liquid state is condensed because the intermolecular forces are strong enough to have the particles stick. I have to put in energy to separate that distance. Think of it as pulling apart the magnet, right? If I create a greater distance, that's a greater potential energy. How do I do that? I have to put energy in. Well, how do I do that? I put heat and it separates the particles, right? You can think of, you know, how do I give a boulder, right? How do I give a boulder potential energy on this hill? Well, someone has to roll it up. Well, it's the same thing. If I want to boil something and give a greater distance between the particles, more potential energy, I have to put energy in the system to separate them. That's what boiling is. I put heat in. So we can see the boiling point of different substances, okay? And the way this is lined up is we see that boiling point increases. Now, why? The dipole moment, the Dipole, is a way to measure polarity. So what we notice is as the polarity of a molecule increases, so polarity is increasing here because the Dipole, a measurement of the dipole moment, increases, we also see that the boiling point increases. So that shows a direct correlation. The more polar something is, the higher its boiling point. Why? The more polar it is, the stronger the intermolecular forces are and the stickier the compounds are. So the harder it is to separate them because they want to be close because they're stickier. Well, what about hydrogen bonding? Because people always hear hydrogen bonding. It's the most common intermolecular force that's discussed, especially in biology, okay? So it's basically a dipole-dipole. And again, the dipole-dipole is basically, you know, a dipole moment aligning with another dipole moment so that the opposite partial charges align. So it's basically polar molecules aligning themselves so that the opposite poles are aligned. Well, hydrogen bonding is just a super dipole. So why is it a super dipole? You have hydrogen that's covalently bound, polar covalently, not nonpolar. So it's polar covalently bound to one of the three smallest atoms that are electronegative, and that's fluorine, oxygen, or nitrogen. So because the atoms are small and they're very electronegative, the hydrogen in that atom can get really close. Now, why is that important? We just talked about, well, the whole point of boiling something is to separate them. But if they're really close, right, that attractive force will be stronger. Think of magnets. The closer they are, the harder it is to separate. So if I have a small electronegative atom and it gets really close to a neighboring molecule, it's going to be harder to separate it. And we see in this, you know, example with water, right? So we have hydrogen and it's bound to a really small oxygen. Remember, fluorine, oxygen, or nitrogen. So basically you have to have hydrogen bound to one of these. And in water, you see that happen 2 times. So it creates this super dipole. I have an extremely partially negative oxygen that has these lone pairs. It's rich in electrons. And then this hydrogen, where the electrons are being pulled away from this oxygen in this molecule, is extremely positive. You can think of it, right? If a hydrogen atom is just a proton and an electron. If the electron's being pulled away from the oxygen in the covalent bond, all that's left is a proton. If you pull away an electron from a hydrogen atom, all that's left is a proton in the nucleus. So this is a very positive partial charge. So now it sees this lone pair that's electron rich, And that gets real close and strong. So that's why hydrogen bonding is so strong. And that's why water, for such a small particle, its molar mass is very small. Typically, when there's an increase in molar mass, you have a higher boiling point. But water has a very low molar mass, but an extremely high boiling point. Why is that? Because hydrogen bonding is so strong. So here's an example, right? So here's that hydrogen fluoride. It's extremely strong, right? Here's, if I take the hydrogen fluoride, will it dissolve in water? Yeah, it's very soluble in water. Why? Because it can hydrogen bond. The hydrogen in the hydrogen fluoride is extremely attracted to the oxygen in the hydrogen. Why is this considered hydrogen bonding? Well, the oxygen's bound to a hydrogen, so it's an extreme negative charge. The hydrogen in this neighboring hydrogen fluoride is bound to a fluoride, so it's an extreme positive. Remember, if I have hydrogen bound to a fluorine, an oxygen, or a nitrogen, I can have hydrogen bonding. Now, if I look here, ammonia, what do we see? Nitrogen's bound to a hydrogen, so this is extremely positive. This nitrogen's extremely negative. It has this lone pair that it's attracted to. So there you go. Okay. Will ammonia dissolve in water? Yes. This hydrogen is bound to a nitrogen and is like a positive charge. This oxygen is bound to a hydrogen, so it's like a negative charge. So this can exhibit hydrogen bonding between these neighboring molecules. So the hydrogen's attracted to the lone pair of this oxygen. Now I could have another hydrogen right here in ammonia attracted to this lone pair. So I could have this right here, this water molecule with the two lone pairs hydro bonding intermolecular force to two neighboring ammonias. And then the hydrogens on this oxygen, now let's draw it a little bit. Let me get rid of that. Now these hydrogens in this water, remember, they're like positive charges. They see a lone pair on a neighboring ammonia, and now they're attracted to the lone pair on neighboring ammonia. So this water molecule is actually interacting with 4 ammonias. How come? The 2 lone pairs are interacting with the hydrogens in 2 neighboring ammonias, and then the hydrogens in the water are interacting with the lone pairs to 2 neighboring ammonias. Okay, so what you see is, you know, the actual water is undergoing 4 hydrogen bonds, so it's really strong. Okay, and then we see here, you know, you can flip this around. It really doesn't matter the interaction with the lone pairs. So hydrogen bonds are found pretty much everywhere. And in biological systems, they play an important role. So I just like to show the example of the double-stranded helix structure of DNA. We see that the nitrogenous bases actually exhibit hydrogen bonds. So here's a hydrogen that's attached to a nitrogen in this nitrogenous base. And then the neighboring nitrogenous base, you see the nitrogen here, is hydrogen bonding. And then here's an oxygen in this nitrogen base, but then the neighboring nitrogen base in the double-stranded DNA has a hydrogen that's attracted to that. And that constant interaction keeps the 2 strands tight, and obviously it has a right coil, and that's a whole other lesson, but that's why that's such a strong interaction. You also see hydrogen bonding with proteins that help stabilize tertiary and quaternary structure. That's a bio class, but I'm just emphasizing how important hydrogen bonding is outside of just solution chemistry. So we talked about the dipole-dipole, which is basically where I have small polar molecules. Then I have hydrogen bonding where I have a super dipole because you have the hydrogen bound to a really small oxygen, nitrogen, or fluorine, which are electronegative, really electronegative, and they're small and they can get real close to that hydrogen. The last but not the least is the dispersion force. And that's the reason why I say not the least is all molecules exhibit dispersion forces, even though it's considered the weakest type of intermolecular force. It actually can get fairly strong as we get larger and larger molecules, and you'll see that in this discussion. But basically, your London force is in every molecule, there's protons in the atoms, right, in their nuclei, and then there's electrons in the orbitals in the atoms surrounding, let's say, the central atoms. So there's this constant interaction, okay? So because we've learned that electrons are moving around in these orbitals, we see that there's always changes in electrons' locations. And those changes are referred to as, they're not permanent dipoles, like with the polar molecules that we talked about, dipole, but we have these little instances where the electrons are moving and they create this pseudo charge, this partial charge. So the best way to think of it is, think old school 35 millimeter camera where you're taking pictures, okay? And I'm taking pictures of a helium atom. So helium, we know, basically has 2 neutrons and 2 protons in the dense nucleus. So the protons are in the nucleus. The nucleus has a positive charge. Now, because helium is a neutral atom, it has 2 electrons. So the 2 electrons are in the 1s orbital. That's why it's a 1s2 electron configuration. And they're going to try to get close to the nucleus because that's where the positive charges are. And we see, you know, here are my electrons, and in here I have my 2+ nucleus. They're going to get close, but for the most part, because the electrons repel each other, they want to stay away, okay? So in that first snapshot, I get this picture. In the next, I get this, and we see, for the most part, the electrons are away. However, once in a while, your pen doesn't work. Once in a while, what you'll notice is now the electrons are maybe on one side. So what does that mean? If the electrons are on one side, okay, right? So I see the 2 negative charges here, and I have the 2 positives. What I'm creating is an instantaneous dipole. So now in this helium atom, there's a partially negative end, and this back part where there's no electrons, just the nucleus, is a partially positive end. Now, that's an example of, just for one instant, I have a dipole. It's not permanent, like in a polar molecule, right, where we have dipoles. It's just an instant, okay? But if it so happens that a helium atom is next to another, and there's this instantaneous dipole where the electrons move to one side, for a neighboring helium, it's going to cause those electrons in their orbitals to move away. And that is what's referred to as an induced dipole. So we'll say that, you know, here I have an atom. It has an instantaneous dipole resulting in a negative and a positive end. Well, because this is positive, that's going to cause and pull the electrons over here and create a negative end here. So basically, and I should have started here, if I have, you know, a negative end in this neighboring molecule and a positive end, it'll push the electrons away and force a positive end here and a negative here, and that's an induced dipole. So instantaneous dipoles force movement of electrons because that's what electrons do. They move in these orbitals, and they can induce dipoles. So how do we determine dispersion force strengths? Well, because we know electrons can move, right? If they move easily, that's considered you're polarizable. So basically, the more polarizable you are, the stronger your London dispersion force is. Basically, what it boils down to is the more electrons you have, the easier it is to move them out, especially as they get further and further away from the nucleus and they're in these outer principal energy levels. Now they're so far from the nucleus, they move around a lot easier. They're more polarizable. So larger atoms, right? So if I have more protons, that makes me larger in mass, and it also stacks the electrons in more energy levels. Larger atoms have larger electron clouds, orbitals, further away from the nucleus, so they can be moved around easier. That makes them more polarizable, and that means I can move them around. Those instantaneous dipoles go up, so I'm going to have a stronger dispersion force. So larger molecules have stronger dispersion forces. So we see this in this nice depiction of here we have the noble gases, group 8A. And all of these are stable. What that means is their S and P sublevels are filled. They tend not to form molecules or bonds, but we notice as their molar mass increases, right? Why does their molar mass increase? Their nuclei have more and more protons, okay? Well, if I have more protons, I got to fit more electrons around it, but now, you know, electrons repel, so I have to go further and further out. So what I notice as I go further out, the electrons are easier to shuffle around because they're not as sticky, they're not close to the nucleus, they're further away. And that increases the probability of an instantaneous dipole. So if I increase the probability of an instantaneous dipole, I'm going to have a stronger London dispersion force. And how can I be aware of that? Well, I can look at the boiling point. Xenon, which has a much larger molar mass, more electrons, more polarizable, more instantaneous dipoles, I have a higher boiling point. What does that mean? It's harder to separate. It's harder to separate these xenon atoms from each other and have them boil. So they have a higher boiling point. We see this also with halogens, right? Chlorine is a gas. Bromine is a liquid. Iodine is a solid. Why is that? As I go down the periodic table in group 7A, molar mass increases. So if molar mass increases, that means that the electrons are further away. Really, with the chlorine, we just have two atoms with a single bond, and because it's a diatomic, this is nonpolar. Okay? This is nonpolar. Whoops, spelled that wrong, I'm sorry. Quality instruction here. I'm not an English teacher. No, okay. So here's my chlorine, and the electrons are being shared equally. However, there could be a case where one chlorine pulls the electrons in the bond a little bit closer, an instantaneous dipole, where I get this partial negative, partial positive just for a moment. And if another chlorine approaches, now that's going to force the electrons away from the partial negative and form a partial positive, partial negative here, okay? Well, what happens when the atoms get bigger, like in bromine? Well, now the electrons in this bond are further from the nucleus, so it's easier to move them around. So because it's easier to move them around, there's more instantaneous dipoles, there's more sticking. More sticking means a higher boiling point, which means, you know what? At room temperature, I'm not a gas, I'm a liquid because I'm sticking better, right? And I get iodine, it's even bigger, right? So now they're sticking so much because of this dispersion force in these instantaneous dipoles that they're in a solid fixed state. So what's the summary of these three? Okay, and we're focusing on molecules right now, not ions. I'm going to get there. But basically, hydrogen bonding is the strongest. So this is where you have the super dipole, because you have hydrogen in a molecule bound to either an oxygen, a fluorine, or a nitrogen. Not in that order, but I did it just, I don't know. It's not in that order. But the hydrogen bonding is the strongest. Then the dipole, this is small polar molecules. And then dispersion, all molecules exhibit it, but especially the nonpolar, this is all they can do. So nonpolar molecules, they can only exhibit dispersion. That's all they can do. Polar molecules can exhibit dispersion, but the dipole is a stronger intermolecular force because it's a permanent dipole, right? Because it's polar. And then hydrogen bonding exhibits dispersion, dipole, but hydrogen bonding's the strongest of that, okay? So dispersion, all atoms and molecules, dipole, polar molecules, hydrogen bonding, molecules containing a hydrogen bound to a fluorine or an oxygen or a nitrogen. So let's do a comparison. So here we have, and we're using molar mass, and with the dispersion, I showed how, as molar mass increases, there's more electrons further away, so it's easier to shuffle these electrons around, make them polarizable, and that increases the likelihood of an instantaneous dipole. So we don't want to incorporate molar mass as a parameter when we're comparing. So what we're doing is we're picking three molecules with very similar molar masses, but we're observing the effect of the intermolecular forces on their boiling point. So when I look with ethane, okay, C2H6, this is symmetrical. This is a non-polar molecule. So the only thing this can exhibit is London dispersion forces. When I look at formaldehyde, this is a polar bond. So that is a polar bond. However, I do not have hydrogen bound to an oxygen, nitrogen, or fluorine. I do not. It's bound to a carbon. So I can only exhibit dipole. And then here I have methanol. Methanol actually has an oxygen bound to a hydrogen. So this can exhibit hydrogen bonding. And what I notice is, right, the higher boiling point indicates a stronger what? Attraction. They're sticking in the liquid state better. It's harder to separate them and create that distance and make them a gas. Well, why does methanol have the highest boiling point? It has hydrogen bonding, the strongest intermolecular force. Why does ethane have the lowest boiling point? It only exhibits London dispersion forces because it's a non-polar molecule. It's symmetrical. So that's the power of understanding molecular shapes and polarity, because now it applies when I look at a molecule and I think of, okay, wait, there's more than one molecule, there's multiple. How do they interact? And the way they interact is how they stick is going to influence whether or not they have a low or high boiling point, whether or not they're soluble in water, right? If it's polar, it's going to dissolve in water. Why? Like dissolves like. Water is polar. If it's non-polar, it won't. So ethane cannot dissolve in water. Ethane will not dissolve in water. Formaldehyde will, but methanol really does. It'll hydrogen bond with water, right? It'll dissolve in a much larger quantity than formaldehyde. So ethane is non-polar. It can only have London dispersion forces. Formaldehyde is polar. It can have dipole and London dispersion, but the dipole is stronger, so it has a higher boiling point, right? Negative 19.5 is closer to 0. If we're on a number line, here's 0, right? It's a lot closer than negative 88. So it's a higher boiling point. And the methanol, right, exhibits hydrogen bonding, dipole-dipole, and London dispersion. So it has the strongest intermolecular forces, and we see the highest boiling point. So to do a quick check, we want to be able to identify, just based on a molecule, right, or an element, because we have a diatomic here, what type of intermolecular force it exhibits. So this is why Lewis dot structure is important. And this is why being able to draw molecules and understand their shape will help you, because you have to identify, is it polar or non-polar, to distinguish between London dispersion forces and the other two. And then you have to determine whether there's a hydrogen bound to an oxygen, nitrogen, or fluorine to distinguish between dipole-dipole and hydrogen bonding. So HBr, what's that? Yeah, so I'm kind of doing easy ones because, you know, we're going to first learn this. There's HBr, right? So what is that? Well, is that a symmetrical molecule? It's not symmetrical. So that means it's going to be polar. So is it going to be dipole-dipole or hydrogen bonding? Well, I don't have hydrogen bound to an oxygen, nitrogen, or fluorine, so it's only dipole-dipole. Sorry, I drew that like that. What about iodine? This is really an element in a molecular form, but because it's one type of atom. So this is a compound, this is an element, but they're still molecular because there's more than one atom. But if I look at iodine, it's symmetrical. So it's London dispersion forces. Carbon monoxide. It is what? Asymmetrical. It's polar. Does it have hydrogen? It doesn't even have hydrogen, so it's dipole-dipole. Now we go to ammonia. What do we see? We see that a hydrogen's bound to a nitrogen, and this is an asymmetrical. It's not symmetrical as a molecule. Why? The fourth group is an electron lone pair, so not all the groups are identical. There's 3 atoms of hydrogen and 1 lone pair. So this is asymmetrical, not symmetrical. It's polar, but more importantly, it's going to be hydrogen bonding because you got a hydrogen bound to one of the 3 most electronegative elements that are small, nitrogen, oxygen, or fluorine. And then you got silicon tetrachloride. Ooh, I'll just do that here. And for the lone pairs, you may see this in the future. People do lines like this. So the line is 2 dots. So really I'm drawing, you know, the lone pairs as just lines. That just makes it quicker. So if I look at silicon tetrachloride, what do I see? Whoa, 4 things attached. They're all the same. This is symmetrical. Therefore, this is non-polar. Even if the bond is polar, it's symmetrical. So it's non-polar. It's dispersion forces. Okay. So now, if I'm looking at these 3 structures, and I'm saying, all right, 2 of these are a gas, and only 1 at room temperature is a liquid. So remember, gases are far apart. The kinetic energy is greater than the intermolecular force strength. Why? Intermolecular force strength isn't that great, so it flies away fast. Liquid, the intermolecular force strength is strong enough to cause it to stick, to have a fixed volume. So of these 3, which one has the strongest intermolecular force? Well, this is a dipole-dipole. Why? It's a polar molecule. We see the dipole going towards the oxygen. What about fluoromethane? Well, it's not symmetrical. It lacks symmetry. Why? There's a fluorine and 3 hydrogens. So there's not all the 4 same thing. So what do I have? I have a dipole there, and it's dipole-dipole. When I look at hydrogen peroxide, what do I notice? Ah, hydrogen bound to an oxygen. What does that mean? An extremely partial positive, extremely partially negative. This is hydrogen bonding. So this is my liquid at room temperature. Okay, so you have to be able to look at the molecular geometry, assess whether it's symmetrical or asymmetrical to identify its polarity, and then figure out its intermolecular force. The stronger intermolecular force, which is hydrogen bonding, will result with the more, condensed state, because there's more stickiness because it's harder to separate them. So I like this one a lot because now I'm looking at groups and I'm trying to figure out, all right, which one has the higher boiling point? All right. So in this first group, all these groups have similar molar masses. So we're not using molar mass because, again, no matter what, an increase in molar mass will increase the boiling point, because as you get more protons, you get more electrons that are polarizable. So all atoms and molecules exhibit London dispersion forces. So that's going to go up with an increase in molar mass. But what we're trying to just focus on is, all right, we have the same molar mass. So we're going to use, whether it's hydrogen bonding, dipole, or dispersion force that predominates and gives it a higher boiling point. So if we look, this is actually, the structure is dimethyl ether. Just write CH3. So I wrote it out in structural formula to show that there's a CH3 and a CH3 sandwiched in between an oxygen that has two lone pairs and then the bonds of the two carbons, and it has a bent configuration. This bent configuration means it's polar, right? Here's propane. It's all tetrahedral, but it's very symmetrical. So because propane's symmetrical, what do we notice? It's non-polar. So this is London dispersion, and this is dipole. So, sorry about that. We notice that the dimethyl ether, or the methoxymethane, you don't need to know that nomenclature for this course because it's organic, has a polar oxygen. Therefore, it has a higher boiling point. And negative 24 degrees Celsius is closer to 0 than negative 42. So what about the methyl amide here? Okay. So the N-methyl methanamide, which again, you don't need to know, but in this structure, what's going to be stronger? Well, that has what? A polar nitrogen. The way this looks, basically, and they're trying to show you there's a methyl group, a CH3 group here. That's basically a carbon with the 3 hydrogens. You then have a hydrogen here, and then you have a CH3 group here, and you have a lone pair, okay? So what happens? Well, not only does it have a polar nitrogen, it can do more than just dipole. It can actually hydrogen bond, because we see that there's a hydrogen bound to the nitrogen right there. So now that goes up quite a bit. And now when we compare ethanol with the N-methyl methanamide, the methanol wins. Why? You'd have more hydrogen bonding. So see how I drew the structure here? What I noticed with methanol, the reason why they write CH3, CH2 is here's a CH3, need 4 bonds to another carbon. Here's my CH2, so here's my CH3, CH2. This is good for multiple central atoms. Then I have my oxygen with the lone pair, and then I have the hydrogen. So someone might say, well, I understand that this is hydrogen bonding and this is hydrogen bonding, but why is this more hydrogen bonding? Well, with this structure, right, the N-methyl methanamide, the hydrogen right here can be attracted to the lone pair of a neighboring molecule. So there's one. And then you could have another hydrogen bond with the lone pair to a neighboring hydrogen. So within one molecule, the lone pair can hydrogen bond to a neighboring hydrogen, similar molecule, or the hydrogen can hydrogen bond with a lone pair to a neighbor. With this structure, I have two lone pairs. So I could have two hydrogen bonds right there. With neighboring hydrogens. And then this hydrogen can hydrogen bond to a neighboring lone pair on an oxygen. So I could have three lone pairs in one molecule. So here's my one molecule. Oh, I forgot to write. That's why they write OH. So here's the CH3. Here's the CH2. Here's my OH. The OH group has two lone pairs that can hydrogen bond to neighboring hydrogens. And then it has a hydrogen that can hydrogen bond to a neighboring oxygen's lone pair. So that's 3 H bonds versus 2 hydrogen bonds. So as you can see, molecular geometry is extremely important. If you go on to any type of organic or biochem where you're learning about solubility, the macromolecules and their tertiary structures, you'll see more and more how intermolecular forces influence that. For general chemistry, we see how it influences not just boiling point and melting point, but it'll influence and solubility. It'll also influence viscosity, how slow something pours. So if something has a really strong intermolecular force, it slips and slides slower because it's stickier, right? So then it's more viscous, surface tension. So that protective layer at the skin, evaporation, all those things are influenced by intermolecular forces. So thanks for tuning in. I hope you enjoyed the lecture and talk to you next time. Thanks.